Well, hello and welcome to the seventh of our NASA Engineering and Safety Center Guidance, Navigation, and Control webcasts. I'm Neil Dunn, the NASA Technical Fellow for Guidance, Navigation, and Control, and I'll be your moderator for today's webcast. The idea to have these hour-long webcasts originated from the members of my NESC GNC technical discipline team, who thought they would be a good way to broadly share their individual knowledge with the rest of the NASA GNC community of practice. We're planning to routinely hold these webcasts on the third Wednesday of every other month at the same time, 2 p.m. Eastern. I'm now pleased to introduce today's speaker, Dr. John Crassidis, who's a professor of mechanical and aerospace engineering at the University of Buffalo. He earned his PhD in 1993 in the field of mechanical and aerospace engineering. At the University of Buffalo, Dr. Crassidis teaches courses including guidance, navigation, and control, optimal control systems, optimal estimation methods, and systems analysis. John serves as the Director of Graduate Studies and as the Associate Director of the Center for Multi-Source Information Fusion at the University of Buffalo. His research interests include spacecraft attitude determination and control, formation flying guidance and navigation, robust nonlinear control, and vehicle attitude dynamics. I'd like to point out that John is also a member of my NESC GNC technical discipline team. The complete version of John's biography is provided on the webcast registration site for your reference. John's talk today is entitled An Overview of Spacecraft Attitude Determination and Estimation. At the end of John's talk, we'll reserve 10 minutes for a question and answer period that I will moderate. And at this point, I would like to turn the webcast over to John. I hope you find this talk informative.
Okay, good afternoon, everyone. So as Neil said, thanks, Neil, for the introduction. The title of this presentation is An Overview of Spacecraft Attitude Determination and Estimation. I always say it's a bad idea to give a professor a microphone, but because I'm going to talk a lot today, and there's going to be a lot of equations, but I have 100 and some slides, but I'm going to blast through the initial set of slides because that's really just an introduction on attitude kinematics, and hopefully that's just a review for everyone. So I really want to get to the point where we actually talk about attitude determination and estimation. So let me give a quick brief review of attitude kinematics. First of all, the matrix inverse is pretty straightforward. You just take the adjunct divided by the determinant. And we'll move to the next slide. And the determinant, as everybody knows, of a matrix has some useful properties, which I listed there. So all these early slides I just put in there just for when we load this up, you'll have for completeness sake. The one that we're really going to focus on is an orthogonal matrix, and that has a nice property that its inverse is given by its transpose, and its determinant is plus or minus 1, and we've got a little proof there. It's going to be plus 1 for what we're going to deal with, and that's for right-handed systems. The cross product matrix is a neat one because that one shows up a lot in attitude kinematics dynamics, and you're going to see that in the attitude determination and estimation portions as well. What this does is you can take a cross product of two vectors, x and y, and instead of using whatever method you do it, you can do it taking a 3 by 3 matrix, which is defined by the cross product matrix. That's given by that x cross matrix, which is defined at the bottom. So you have a 3 by 3 matrix, which is a skew symmetric matrix times a 3 by 1. And anybody that's done attitude kinematics or dynamics, they've quickly gone to the point of memorizing this matrix. So it's a useful matrix, and you'll see where this pops up later on. Moving on to the next one. As I said, I got some stuff here just for introductory sakes, but there's some neat properties for a cross product matrix. Eigenvalues and eigenvectors, straightforward. I think everybody understands that. So when we talk about attitude determination, I'm going to talk about how we determine the attitude. So first I want to talk about what the attitude is. And one of the most common ways to talk about that is the direction cosine matrix. And it describes a rigid body relative to some reference frame. So if we look at a reference frame, like stars are inertially fixed for the most part, but for most spacecraft missions you can consider them to be inertially fixed. So you define some frame that doesn't move in space, and then you can know the location of those stars with respect to that frame. And then you can form a vector to that star in that reference frame. And then you have a star camera on board your spacecraft, which measures the same exact frame because the star is essentially an infinite point away. We don't have to worry about parallax. So that measures the same exact vector that we described in the reference frame, but now in body coordinates using some body frame that we've defined on the spacecraft. So now we have a reference frame N1, N2, and N3, and a body frame B1, B2, and B3, and we want to know what the relationship is between those. So because These are both orthogonal right-handed frames. We can write B1 in terms of N1 components, N2 and N3, and we can also write N1 in terms of B1 and B2 and B3. So if we go on from there, if we take dot products of N1 and B1, we can solve for what A11 is, and that's just the dot product of N1 and B1. And continuing like that, we can see that the primes and the 1, 1, 2, 2, and 3, 3 are all equal to each other. And if we take other dot products, we can see that the A12 element, backing up to the slide, is equal to A21 prime, and that has some relevance later on. Okay, so it's called direction cosine matrix because you're looking at the cosine angles to get the information how we map one vector in, say, B1 into N1, N2, and N3 coordinates. Now, if you continue on there, you'll find out that the A prime matrix, which is the component of those A elements, is the transpose of the A matrix. And that's why we talk about orthogonal matrix, because the direction cosine matrix is orthogonal. And that's going to have some nice properties associated with it. And then you can, again, this is just review material, so I'll just skip some of this stuff. But the bottom line is, once it's all said and done, the inverse of the attitude matrix is given by its transpose. So it's thus an orthogonal matrix. So let's say now I've got some vector that I'm walking along the B1, B2, and B3 coordinate system, and I have the same vector described in N1, N2, and N3. So now what's the relationship between how I can describe, instead of keep writing B1, B2, B3 in vector and N1, N2, and N3, can I make this a little simpler? So that one thing I keep stressing here, it's the same exact vector. It's that vector that to that star, one's described in inertial coordinates and the other one described in body coordinates. But it is the same exact vector, one again in inertial, one in body. So that's why I didn't put anything in front of that R, because I haven't defined what coordinate system it's described in yet. Okay, if you go through some of this math, what you end up with is down in matrix form is you can write the components that you walk along the B frame as in a vector B1, B2, and B3, and you get the same exact relationship. That's equal to the attitude matrix times the components that you walk along the N. So that simplifies the notation tremendously. So we don't have to keep writing B1, B2, B3 vectors. We can just write the components itself. And this is the main equation we use for attitude determination. The N vector is the reference vector. That is something that's usually known, and the B frame is usually something that we measure either with a star camera or whatever hardware we have, and I'll talk about that later on. The nice thing about the attitude matrix is if you do sequential rotations, so if I rotate from one frame to another frame and then rotate to a new frame, and then do some substitution, I get that Z is equal to A2 times A1. Well, since Z is a right-handed orthogonal system and N is, then A2 times A1 must be an orthogonal matrix. So anytime I multiply orthogonal matrices, I always end up with an orthogonal matrix. Okay, so looking at attitude parameterizations, the attitude matrix is one way to do it. There's many parameterizations. I encourage you, there's a great review paper by Malcolm Schuster, I think it was in 91, I think it was published in the Journal of Astronautical Sciences. It's a great paper to look up attitude parameterizations. Basically, they're all equivalent, and each has its advantage and disadvantage, and you'll definitely see that when we get into attitude determinant estimation. Quickly, everybody, just a review of Euler angles. It's one way you can do this. So if you do a sequence of roll, pitch, and yaw, and the first rotation I do is about the N1 axis, and I call that the roll, and I can write equations for N1 prime, N2, and N3. It's very simple. And I do the same thing. I rotate about the new N2 axis, and then I rotate by the new N3 axis, and that gives me my full entire sequence. And I substitute, and I can backfill the attitude matrix, and that's given by the bottom there on page 22. So that's very simple. Euler angles are nice for physical properties because, sitting in the plane, you get a sense of your roll, pitch, and yaw. They give you a nice physical feel, but there's some bad news about them. First of all, they're highly nonlinear. See a bunch of sines and cosines there, so that's one of the bad things about it. And they're also, I'll talk about this in a second as well, they also have singular properties. There's 12 possible combinations, so I rotate about the one axis first, and then the two, and then the three. I can also do the six asymmetric. I can rotate about the first, then the third, then the second. The six symmetric, I can do a 3, 1, 3 as an example. WMAP spacecraft. Most dual spin spacecraft use symmetric because that gives a much nicer feel for that. And so that's why I said the Euler angles are nice because they give a nice physical feel. And you can also extract the Euler angles from the attitude matrix, always using some equations. But if we back up a second, one thing I'll mention, let's back up to, if you look at the attitude matrix, and assuming that all the angles are small, the sine of the angle is going to go to the angle and the cosine is going to go to 1. What you end up with is this nice linearized matrix that the attitude matrix is approximately equal to this matrix that's shown in the middle here. That's equal to identity matrix minus this cross product matrix. So here's your first look at, again, why cross product matrix shows up everywhere. So phi theta MC, you end up as this vector alpha. You set up this cross product matrix, and you can write the attitude matrix as I minus alpha cross. That actually is the first order approximation for the attitude matrix. You can take it to higher order as well as a series expansion on sines and cosines. But this sort of expansion is what we're going to be used to driving the covariance later on for the attitude determination portion. Okay, another way to do this is Euler axis and angle. So Euler's theorem states that the most general rotation of a rigid body is with 1 point fixed is rotation about some axis. That axis is called E hat. I put an E hat only to denote that it's a unit vector, and some angle, put var theta to distinguish it from theta because it's not related to anything in an Euler angle. So if we go to the next slide, this gives you some of the geometry. Again, I'm just doing this for review. But the bottom line is, after you do some more math, you can show that the attitude matrix, I could show it right here, in terms of the Euler axis and Euler angle, is given by the A matrix showing up above there. Now, if you take A and multiply it by E, you get E back. So that shows us that one eigenvalue of the attitude matrix is at least 1. And there's 3 cases there shown, and I'll let you just go through that for the eigenvalues of A. That has some physical significance, which I'm not going to mention too much here. If you let sine theta go to theta, var theta, and cosine equal 1, that's the first order approximation. So you can now relate the Euler axis angle to the attitude roll, pitch, and yaw for small angles. Okay, what we really do a lot in, and I know that there's information on quaternions on the NESC website, so, but basically, quaternions are the most important thing what we do because they have some nice properties. They were first described by Hamilton in 1843 using hypercomplex numbers, although we don't need to use hypercomplex numbers to do what we're going to do for today's talk. I always like to put a little history. Lord Kelvin hated quaternions. His exact quote was, "Quaternions have been an unmixed evil to those who have touched them in any way." Gibbs was also not fond of them. He had also his representation. Hill had a better impression of them. Modern day uses exclusively used mostly on spacecraft because they're nice properties, and I'll talk more about that as we go along. So I talked about the Euler axis and angle only to introduce quaternions. So quaternion is a 4x1 vector, but we really should think of it as a 3x1 vector and a scalar. And the 3x1 vector is the axis times the sine of the angle divided by 2, and the scalar is the cosine divided by the angle divided by 2. The nice property about this is if you go through all the math on how to get the attitude matrix, it's given by that last equation. So if you look at that last equation, it's quadratic in the quaternion. So I don't get anything really it's nonlinear, but it's nowhere near as nonlinear as the sines and cosines. So that's one of the neat properties, that it's quadratic in the attitude matrix. Another way you can write this is you can write it as a product of 2 matrices. This matrix C is given by a 4x3 matrix. Again, that cross product matrix shows up. And C is the same thing. So I put a minus sign in front of the cross product matrix. But if you write this, if you could see, if I substitute Q with minus Q, I get exactly the same attitude matrix. So that's kind of one of the bad things of the quaternions is there's a 2-to-1 mapping that Q and minus Q give you the same rotation. And when I say that, when you program this quaternions up in an actual spacecraft mission, you have to be very careful when you get a sign flip in the quaternion. That's something that you have to worry about in attitude estimation, but definitely more on the control side of things. So I went on and explicitly wrote out the parameters there on how the attitude matrix shows out in the for each one of the components there. And then you can extract, if you're given the attitude matrix, you can extract the quaternion components. Okay, and and this paper by Shepard will give you a nice way to extract out, because if Q core is equal to 0, go back here, you end up with an issue. Oops, I'm sorry, right here. But Shepard wrote this paper to extract out quaternions. So the identity of quaternion is when I set the first 3 components equal to 0 and the fourth equal to 0. That, if I substitute that back in the attitude matrix, I get the identity attitude matrix. The inverse quaternion, and this is just notation, is you can't take the inverse of a vector, but this is just notation to say I'm taking the quaternion inverse. And that all is, if I substitute the negative of the vector part in, I get the transpose of the attitude matrix. So that's kind of nice. Quaternion multiplication, I can multiply 2 attitude matrices and extract its quaternion, or it's easier to just use quaternion multiplication. This is just notation. So I'll multiply 2 attitude matrices, 2 quaternions, Q prime and Q. I can form this 4x4 matrix using the matrix Q involving Q prime, or using the matrix C involving Q. So it's a bilinear relationship. Now I'm going to stop here and interject quickly to state that this is actually, when Hamilton originally did this, if you do this using hypercomplex numbers, the quaternion multiplication that he defined is that in the opposite order of the attitude matrix. You see in the top here that have A Q prime times A of Q, and I have Q prime times Q. In Hamilton's original convention, it would be Q times Q prime. Schuster redefined this in 1981, so and the spacecraft community generally uses Schuster's. But with that being said, just be careful on what, if you read papers or whatever you're doing on the work, this is a still used Hamilton's convention. Okay, one thing I didn't mention was that the quaternion norm has to be, the norm of the quaternion must be 1. I thought I had that some up here. Yeah, so if I take that's the vector part squared, so I get sine squared plus cosine squared. That's one of the bad things about the quaternion, is that its norm must be 1. So I have to enforce that. If I use a small angle approximation, then the nice thing about that is the scalar part goes to 1 and the vector part goes to half angles. So a lot of times whenever we talk about quaternions and small angle approximation, you always hear that word half angles being said. What that means is that the vector part of the quaternion is equal to half angles of the roll, pitch, and yaw. And that has some physical meaning, which I'll talk about later on. Okay, and then so I talked about, for small angles, the attitude matrix is I minus this, now I'll call it delta alpha cross. What does that mean for the quaternion? Well, it means that the vector part goes to 1 and the vector part goes to delta alpha divided by 2 and the scalar part goes to 1. It's not exactly normalized. It can never be normalized, actually, from a pure mathematical point of view, but it's close if the angles are small, and this has play later on. Okay, kinematics, we have the angular velocity, which is the angular velocity described in body coordinates of the body vector, body coordinate system with respect to any inertial frame. Why that's important is because that's exactly what strap-down gyros give us. And the attitude matrix is given by that equation up there for the kinematics. And it has a closed form solution, which is kind of nice. So let me skip through what the issue is with the Euler angles. The kinematics is given by the central equation there. You see when cosine of theta is equal to 90 or 270 degrees, I get a singularity. This is why we don't use Euler kinematics. For aircraft, not a big deal, especially commercial aircraft. You're not going to be pitching up 90 degrees, hopefully. But for spacecraft, it's going to be an issue. So that's a mathematical given. So what's the problem here? Well, Stupe-Nagel in 1964 wrote this paper that stated that any three-dimensional parameterization, like Euler angles of three-dimensional parameterization, will always have a singularity. So that's the bad news. There's this Gibbs vector and modified rho degrees parameters. They're all three parameters representations, but they will always have a singularity. The advantage of quaternion is it does not have a singularity. So that's so what happens to the attitude matrix when you have that 90-degree condition is, using the simple sine of theta plus c, you lose a degree of freedom in the attitude matrix, which is bad. So that's a kind of equivalent to a gimbal lock for a hardware system. If you go back to quaternion kinematics, and to do some math here, again, I want to skip the details here, but you can see that the kinematic relationship is also bilinear. You can write, that C matrix shows up again. It shows up a lot, actually. So it's 1/2 C of Q times omega, but there's an identity that C of Q times omega is equal to this omega, which is a 4x4 matrix. Again, you see a cross product matrix times the 4x1 vector of Q. And you don't see any single issues here, so that's kind of nice. So that's one big reason why we use that. Another reason is it has a closed form solution, and that's given by this equation here. So in propagation of quaternions on spacecraft for attitude estimation, we always use this nice closed form solution. Okay, so that is a very quick review. I did it in 20 minutes of attitude kinematics. So I want to now get into the meat of it, and that's attitude determination. So obviously it's important because in a university setting we talk a lot about controls, and we talk very little about estimation, but my statement is you can only control a spacecraft to within of how well we know its knowledge of where it's pointed. So oftentimes the estimation portion of it is neglected. And it's obviously the most important thing, because you really can't do fine pointing of a spacecraft if you don't have fine knowledge of where it is. So with that being said, you generally don't measure the attitude directly, with the exception of something like Earth sensor, that if you're looking at the Earth, you should point to, you can use an Earth sensor to do that. But that might not give you the accuracy. Just before I had this talk that we were talking with Neil about my days at NASA and talking about GOES, they used an Earth sensor and it wasn't meeting the requirements, and it had to eventually go to a star tracker. So as I mentioned before, the reference vector must be given, and for star cameras, it measures there's two basic ways. There's ECDs and CMOS devices, but basically with the focal length of one, which you can always assume you can end up with, you measure alpha and beta, and that's important. I'll talk about that later on. You don't measure B directly, but you can form this in to get this B vector. And some sensors are similar to star trackers. 3-axis magnetometers measure 3 axes of the attitude, but they don't give you 3 axes of information. They'll give you 2 at one time. Obviously, nowhere near as good as the stars, because we don't know the magnetic field as well as we do the reference of the stars. So that's something that's updated every 5 years. IGRF is a very common model. Earth horizon sensors, I'm going to skip through a lot of this stuff, but basically you scan the Earth. GPS sensors are the one that's a little bit different. They don't follow that model of B is equal to A times the reference vector. What this is, you've got 2 wavefronts coming through. You also have an integer ambiguity problem that you need to determine the integer to get the fractional part. That's a big problem with that, because you can have cycle slips. But once it's all said and done, you're essentially measuring an angle, and that's given by this delta phi. So that has a little bit different measurement model to it. We wrote a paper, Linus Markland and I wrote a paper to put that into a form that looks like the B is equal to A times S. So you can get it into that form under certain conditions. And usually those conditions you can usually do, 99% of the time you can do. And here I put a whole bunch of things of error sources, which I'm just going to skip this. So let's get to the meat of what I really want to talk about today. So let's say if I measure a vector to a star, that only really gives me 2 out of 3 information that I need, because I don't know the rotation about that vector. Okay, so I need at least 2 non-collinear vectors to get this information. Actually, that's kind of the minimum, but it's really not. I can get away with using 1 vector to a star. That gives me 2 pieces of information and then 1 angle. So that'll give me the 3 if I really wanted to do that. But let's look at this from a point of view that I get a whole bunch of stars. So I've got B1 and N1. First I have to do a star pattern recognition. There are whole papers written on that. That's been a subject that's been studied, and that's been very well solved now. Daniel Mortari at Texas A&M has written some really nice algorithms that could do this really quickly. So once I identify the stars, I have them in my catalog, and I can get the N1 and N2 vectors. And then I measure the B1 and B2 vectors. So the simplest algorithm to get the attitude is a so-called triad vector. And the way you do this is you construct these 3 vectors, C1, C2, and C3, D1, D2, and D3. And then I use this neat identity here for the cross product because the attitude matrix is orthogonal. The determinant's equal to +1 for a proper means I'm using right-handed systems. And I can go through some of this math and show that the DI vectors is equal to A times the CI vectors. So now I can take all my D vectors and C vectors and put them in a matrix, and from that equation 1, it follows that the D matrix is equal to A times the C matrix. Since C is also an orthogonal matrix, then its inverse is given by its transpose, and I could get the attitude matrix is equal to D times C transpose. And that's a simple algorithm, but it's not optimal, and that's something that Malcolm Schuster showed, that it's ignoring some of your information. You actually want to use your most important vector, most accurate sensor first to form this matrix C and D here. But here's an example here for N1 and N2, and then I took some attitude matrix and I computed C and D, and I get that attitude matrix, and this is noiseless. There's no noise associated with it. So if I take A times N1, you'll get B1 exactly, and the same with A times N2. Okay, that's kind of nice. Really, what Grace Waba in 1965, she's a statistician, probability person, still active, posed this problem in 1965. And what she said was, in this IM journal, she said, okay, I want you to find the attitude matrix. Say you have a whole bunch of observations, and each with a weight, and we'll talk about the weight in a second. And I want you to find the attitude matrix. Well, this is actually a simple least squares problem, but she threw this little caveat out there, subject to the constraint that the attitude matrix must be orthogonal. So if you go and multiply this loss function out, what you see is you end up with a term that doesn't depend on the additives, B1 dotted into it, BI dotted into itself. The second term is one that depends on the attitude matrix. The third one, we use the constraint, and that disappears. So all we're left with is this minus sum of the B dotted into A times N plus terms that don't depend on A. And so she posed this, and there were a whole bunch of solutions that came out. But I want to talk about the one that Davenport did, and that is using the attitude matrix. And for some reason, they decided to put a negative sign early on, and instead of minimizing, they maximized this loss function. So maybe they get rid of the negative sign, but that's I'm just going by historical what happened in history here. So it's no big deal. You just take the negative sign of the loss function and you turn minimization into a maximization problem. So now we want to maximize that function right there. That's a function of the attitude matrix. And what Davenport did was he parameterized it using quaternions. And I went through and I actually simplified this a little bit to look at the derivation. So I'm going to substitute the attitude matrix as C transpose times C into J of A. And now I'm going to solve for the quaternion. Okay, so that's equation 2. And I also have, there's some also neat identities here. I already talked about C times some vector is equal to omega times that vector. There's also another one for psi, which is psi times the vector is equal to this gamma times this vector. So I use those identities into equation 2. Just the neat properties about these matrices, they're skew symmetric, and they also commute, so omega times gamma is equal to gamma times omega. But if I use these identities into equation 2, I can actually pull out Q on both sides of the attitude matrix. So Davenport had a much more complicated expression for this matrix K. I like this one because I think it's easier to see. So the B's are given, the N's are given, you can form this matrix K. And you can pull out the Q's using the identities that I showed before. So that the whole loss function blasts down to J of Q now. It's only a function of the quaternion. But now I'm subject to the quaternion constraint. So how we handle that, we do a Lagrange multiplier with the constraint. That's equation 3. Okay, so that's what we're working with. So Davenport recognized that, looked at this loss function and said, hey, I got something really neat here. It's quadratic in the quaternion, so I should be able to get an analytical expression for a solution for it. And that's what he did. So if I take the partial with respect to Q, I end up with KQ is equal to lambda Q. And what we realized was this is exactly an eigenvalue eigenvector problem. So Q is actually an eigenvector of K, and lambda must be an eigenvalue of K. So if you go back to this and substitute KQ into the loss function, you'll find out, so just take KQ and substitute it into equation 3. KQ is equal to lambda Q. and Q transpose times Q is 1, so that disappears, and all you're left with is lambda. So the loss function blasts down to just lambda. So if you want to maximize this, there's 4 eigenvalues that you have and 4 eigenvectors. Which eigenvector do you pick? The eigenvector you picked is associated with the maximum eigenvalue, and that's what is so-called the Q method. Now, unfortunately, this was never published. This was actually published first in a CSC report, I think by Keat, as an appendix. So this was neat. It's a great solution. It takes everything in it that you have, all the information, not just 2. So if you have more stars, and you can also weight them, and I'll talk about the weighting in a second. But at the time, it wasn't practical because no processor can do an eigenvalue-eigenvector decomposition. So in 1981, Schuster wrote his first famous paper in attitude estimation. And he always had great acronyms. He called this one the Quest algorithm, the quaternion estimation. So what he found was a solution that didn't, he took Davenport's essential beginnings of that and found a solution that didn't have to do the full eigenvalue-eigenvector decomposition. And that was the first practical algorithm that allowed us to put on spacecraft. And there's a whole bunch of historical papers that are out there that Malcolm Schuster wrote, and I can certainly give those to load on the website. So now if we do the same exact example I had before, and I can form this K matrix, and it's given by the matrix there, and I do an eigenvalue-eigenvector decomposition, you can see that the maximum eigenvalue is the 4th one, so I pick the 4th eigenvector, and I compute it, add it to matrix, and I get the same exact solution that I got using the triad method. The reason why is because I don't have any noise here. Okay, so as I mentioned before, we don't measure B directly. So let's look at the star tracker example. What we measure is alpha and beta, and that's where the noise occurs. So if you look at the stellar collinearity equations, I can work with alpha and beta, but it's very difficult to back out the attitude matrix because I got the elements of the attitude matrix in the numerator and denominator. That's why I prefer the B is equal to A times N model versus working with the collinearity equations directly. I can do it, but then I have to use nonlinear least squares, and I'd rather not do that. Well, what the problem is that I add noise to, in Mathematica, I would add noise in the hardware. This is where the noise comes in. It comes in alpha and beta, not in B. When I stick, if you have Gaussian noise on alpha and beta, when I go through this transformation in the top equation, it no longer is Gaussian. It can't be. So that's a little bit of a headache. So here's a common model for a focal plane detector. On the noise model, it's a correlated model. And it realistically shows that the errors increase as they go away from the bore site. But as I mentioned, you don't want to use those collinear equations directly for attitude determination. So as I mentioned, the noise is no longer given by a Gaussian noise process. But Schuster thought about this, and he said, okay, and I'll show a diagram in a second, but let's assume that the noise is small. So that means my B vector in that bottom equation is close to being a unit vector, but obviously it can't be, but it's close. And he assumed that the noise is perpendicular to B, and I'll show you what the ramifications are in this in a second. So what he said was, okay, if the field of view is small, I can approximate let's see if I have the diagram in the next one. Let me jump quickly to this. Okay, we know that noise must lie somewhere in the unit sphere, but he said I'm going to approximate this by a tangent point. So you can see if the angle is very small there around that vector, that the tangent plane approximation is a very good approximation of what the noise is. And what that is it's a projection matrix. That's what it projects. Projection matrix. It projects the B matrix directly on. Well, when I multiply a projection matrix by B, I get exactly 0. So that's what definition of projection matrix is. And so Malcolm said he came up with this in 5 minutes. So basically, if I go back and I can do an expansion on this model here and add noise to this, and the first order expansion, what that noise is, it would be exactly the Quest measurement model, which is given by this over here. Okay. The bad thing about a projection matrix, it's singular, and that's going to cause some headaches, which I'll talk about in a second. So it's a very popular model to use because it's very simple in what we do here. So now, if we want to back out the covariance of, which is something we want to know, how well analytically is our star tracker attitude determination process doing? We want to determine the covariance of it. So we can do this through maximum likelihood. But if we set up the likelihood loss function, the negative log likelihood, to get more specific, it's given by J of A over there. But we end up with this Ri inverse. But Ri is a singular matrix. And the good news is that Malcolm showed that you can effectively replace Ri with a scalar, that's sigma, which shows up in two places. It shows up in this matrix R here, and also shows up in this matrix R here in the focal plane model. So he showed mathematically that you can replace R with a scalar times identity, which I think is one of his greatest results. And there's the paper there. He also did this with the Collin filter, which we'll talk about later on. So without any loss in the mathematics, I can replace Ri inverse with sigma I inverse for small fields of view. Okay, so now what this shows is going back to Waba's original loss function, that the weight, I replaced the weight that she had described in her 1965 paper with sigma I to the minus 2. So that is the relationship between attitude determination backing from maximum likelihood all the way back to how Grace Waba first posed the problem. Okay, so I'm going to rewrite this loss function a little bit, and I'm going to put hats in front of A to denote that it's an estimate. And I want to get the A now denotes the truth, which I don't know. And that's the bad thing I would say about estimation, is I don't know the truth. I'm going to do a first order expansion upon that, and we talked about what that is. It's I minus delta alpha cross. So delta alpha are now the small roll pitch and yaw angles which map, you can think of it as a rotation matrix that maps the true matrix into the estimated frame. So that's something that I want, because the covariance is the covariance of the estimate minus the truth. Okay, so how do I get the covariance? Is that I can now, if I substitute A hat into the above loss function and take the partial with the double partial, or the Hessian matrix with respect to delta alpha, I end up with, and take its inverse, that's the covariance matrix that I get. That'll tell me, so this is a 3x3 matrix. You see the cross product matrix showing up again. The diagonal elements of that will tell me what I expect to see in the roll, pitch, and yaw errors. So that's kind of nice that even though I'm using quaternions, I get a physical feel out of the covariance. It'll tell me I can take the square root, multiply by 3, and give me the 3 sigma bounds, what I expect to see in the errors from the truth to the estimate. So you see here I got A times N, which is equal to B. So what you can do if you want to get mathematical about this, it's really evaluated at the true values, but without loss in any, it's a really second order effects, I can substitute in the measurement directly for A times N. This is really neat, because without ever computing the attitude, I can tell you what I expect to see in the errors, which is kind of a neat result. And then we wrote a paper later on to expand upon Malcolm's original concept of the projection matrix for large field of view sensors, and we showed that if you have a very large field of view sensor, that Malcolm's model will break down. When we show you get 30% better accuracy using our model. So you got to be careful. I always say be careful of the math. Always look at the mathematics. What are the limitations of the mathematics behind what you have? I've seen a lot of people just use sigma squared as 1 over the weight without really looking at the mathematics. It's really important to look at the limitations of what you're doing. So here's a spacecraft that I worked on. So I thought I'd bring this one up. We worked on a contingency mode for the TRIM spacecraft using. We knew the horizon sensor may have some issues. We wanted to develop a contingency mode. It used the sun sensor and the 3-axis magnetometer. In practice, the sun is not available all the time. It's only available for 1/3 of the orbit. But in this case, I'm going to assume it's available all the time. Okay, so now we can get the same thing with the magnetometer. All we need to know is the position, and then we can determine the reference field. That's the inertial field, the 3 components of that. And then I simulated some noise. I put some noise on the on that to get the body measurements. Now this one I put Gaussian noise. That's not realistic. The sensor itself is pretty Gaussian, but the error in the magnetic field is not Gaussian. So the way we handle that is we generally bump up the covariance. So this is kind of getting academic exercise now, but okay, the sun inertial position, we just need to just know time, and we know that. The sun moves about a degree a day, so over 8 hours, you're not going to see that vector move too much. And the sun body vector is given by that. You get the classic roll-yaw coupling there. And so if I take those and I added noise to them and I compute the 3 sigma bounds from that covariance, and since this is a simulation, I know the true errors, so I plotted that versus the 3 sigma bounds, you see some really neat things popping out of this, that the 3 sigma bounds exactly bound the actual errors. So that's kind of cool. That's a very useful tool, and we use that to help look at what we expect to see on a particular scenario. What I want you to look at is to see when it starts to growing, and it's growing and it's decreasing. So what's going on when that happens? Well, if I look at the, so I plotted the error bound, one of the error bounds here, and also looked at the cosine of the angle. Okay, you can see when the cosine of the angle is equal to -1, that means that I have nearly collinear vectors. That means that the sun angle is nearly, sun vector is nearly co-aligned with the magnetometer, magnetic vector, sorry. And that I can compute. I can know when that happens without having using the sensors. I can use the reference frame vectors to know that. So our mathematics are telling us what we expect physically. As the vectors become co-aligned, the errors become worse. And that's exactly what happens here. Every time this gets close to -1 is when the attitude errors start to increase. So that's kind of nice. The mathematics are telling us what we physically expect to see. So that I think is a cool result. And then I did the same thing with the star tracker, and try to use some more realistic scenarios there. And I've got a link there for the code if you want to see that. And I had a minimum of two stars available with a maximum of 4. And I went and did the same thing using that algorithm. And you can see when I get down to 2, the errors increase. When I get down to 4, they decrease. Same kind of thing going on here. I had this star tracker had an 8-degree field of view, so the yaw angle is essentially around the bore site. You can see that the yaw errors are about an order of magnitude larger than roll and pitch. Okay. With star trackers, we tend to put in at least 2 cameras for redundancy, but we also try to make them as orthogonal as possible. Obviously, through physical limitations, that may not always happen, but that'll give us the most accuracy in all three axes. So that's why we try to spread out the star trackers as much as possible. Okay, so that's kind of nice. Let's talk about attitude estimation. So we want to try to overcome this issue of this errors going up and down, and we also want to filter some of the estimates. Now I know Chris D'Souza is going to be talking about column filter, so I'm not going to give a column filter review. He's going to give one in March, so I'm not going to talk about that. The issue is that we're going to use gyro measurements, and then when we do that, and try to get the gyro bias out of it. But when we do that, the equations become nonlinear, so we have to linearize this. If we use the straight extended column filter, which is an additive approach, it's an additive expansion. Essentially, the way you think of this, if I take 2 quaternions and add them, that's no longer a quaternion. Okay, it can work, but you end up with a covariance that's nearly singular. I say exactly, it's actually nearly singular. It's exact if it's a linear constraint. That was something that Bar Itzhak had mentioned to us. A better way to do this is to use a multiplicative approach, where I define an error quaternion, which is the truth times the estimate inverse. Okay. In the attitude matrix, this will say that the error attitude matrix is given by the true attitude matrix times the transpose of the attitude. Now, when the truth is on top of the estimate, then the attitude matrix goes to identity exactly. Okay, so this was actually done in the 60s, and then Lefferts, Markley, and Schuster wrote a survey paper in '82, I believe, in the Journal of Guidance and Control. It was really a survey paper, but they really put the mathematics in a nice way, explained it a lot nicer. There were 3 ways to do it. The first one and the third was Markley and Schuster, and they're both actually mathematically equivalent. I'm going to show you Schuster's approach. If you take a time derivative of that equation, you end up with this top equation up there. We need to find an expression for Q dot inverse, so I'll let you go through the mathematics of that. Once it's all said and done, you end up with this bottom equation. This is an exact equation on this slide. And I've defined delta omega as omega minus the estimate of omega. So the only portion that's nonlinear is that second term right there. And its first order approximation for that is that it's just equal to 1/2 times delta omega and 0. So if I go back and I substitute that into this equation, what happens is the fourth component of the error is equal to 1. Okay, so what that is saying is exactly what we think is, as I mentioned before, that the fourth component goes approximately to 1. So we can ignore that in the column filter altogether and just work with the first three components. And then typically what you do is you divide by 2, so you work with the attitude error space instead of the vector part of the quaternion. Why we do that is because when the covariance that's being spit out by the column filter is exactly will tell us the small roll, pitch, and yaw errors. So that's why we typically just use the divide by 2. So now we have all of our sensors. We have a gyro model as well too. The discrete time simulation, if you're interested in simulating that, that's at the bottom there. Given the spectral densities of that, of the properties of the gyro, and we want to determine B dot is equal to noise. And you're given sig U and sig V usually from a gyro manufacturer. So you want to put in, there's two things going on here. The gyro is helping to filter out the attitude measurements, and the attitude measurements are helping to determine beta, which is generally called a gyro bias because it is a drift, but over small time scales it looks pretty constant. So that's the model there for gyros. So once you go through this process, now you have a linearized extended column filter that's done using a multiplicative approach instead of an additive approach. And so now we can write this in continuous time using this F matrix and G matrix. And then we can do the same linearization for the output for the column filter. We need this so-called H matrix, that's a sensitivity matrix, and do the same multiplicative approach. And we end up with this cross-product matrix showing up again. So now we go through and we can do our standard, well, you can see here I have a delta X state because we're actually estimating is delta alpha, so you have to be a little careful here. You're not estimating alpha, you're estimating delta alpha. So this looks a little bit different. You don't see X plus is equal to X minus as you would in a normal column filter. So you have to be careful of that. If you write it that way, then you have to reset X to 0. And there are a lot of times of resetting in a column filter for attitude estimation. That's what they're talking about. Okay, and then the way you update the quaternion is, like I said, you assume this error that it's 1/2 the error angles and then 1, and multiply and then renormalize it after that. Once it's all said and done, it looks like an additive process, but to within first order, I'm maintaining the quaternion normalization. That's the big difference than starting off by doing an additive approach. If I did an additive approach right from the beginning, I've lost that quaternion normalization right at the first order term. This, within first order, I've maintained the quaternion normalization. So that's kind of why the multiplicative approach. And I've reduced the covariance now from a 7x7 to a 6x6. The last three are the errors associated with the gyros bias. So here's a table of the implementation of the extended column filter. And again, I got this discrete time propagation, which is nice. I also have, there's also a solution for the discrete time propagation of the covariance, which is nice. That saves on the computational effort. I'm not going to go through the mathematics of that, but that's kind of a nice thing there. And then I can also use the covariance for discrete time. This is actually not exact, but it's good enough if delta t is small, which is usually never an issue for attitude estimation purposes. But bear in mind, this is only a first order approximation. Okay, so I went through and I took some standard gyro, I think this is Cyra 2 parameters from gyro. I put an initial gyro bias of 0.1 degrees per hour, and I sampled at 1 hertz. And I gave it a pretty good initial attitude estimate, and the covariance is pretty small there too. I used the same exact stars that I had before. But now, this is plotting the 3 sigma bounds from the extended column filter. You see this bumping up and down just slightly, but not nowhere near as much as before. That's because the gyro is helping out in and determining the and filtering out that aspect of the up and down motion due to the minimum stars to maximum star case. And I've done a significant amount of filtering here. I've gone down to micro radian level accuracy, which is nice. The outliers are still a magnitude order bigger, but they're much smaller using this filtering approach. And then if I look at the gyro biases, it takes about 15 minutes, but I've nailed them pretty well. You can see it goes down to 0.1 degrees. So that's a so-called a complementary filter. Again, the gyro are helping filter out the attitude noise from the sensors, and the attitude is helping to determine the gyro bias. So that's a quick run of that. What I'll mention is that if you look at the strict common filter form, it requires an inverse of a 3n by 3n, so n is the number of observations. Obviously, that's computationally expensive. Morel came up with a really neat idea. It's a quasi-linear. The extended column filter is not a nonlinear filter. It's a quasi-linear filter. And he used this thing to, in a nutshell, he showed that you can start taking an inverse of a 3n by 3n inverse. You can take an inverse of a 3 by 3, which has a closed form solution, n times. And that greatly reduces the computations. So we don't need a general inverse command on the processor. So that's the version that everyone that I've designed, we always fly to save on the computations. And this flowchart here will show you the process of what's done there in Morel's filter. So that's basically what we run on board. So I think that's the end of my time. I'm sorry that was a lot of initially through there, going through things quickly, but I wanted to get to the main part and talk about the attitude determination and estimation. And I also have a whole thing on quaternion identities. I've been keeping a running tab of quaternion identities. I'll be happy to put that up. It's gotten to be several pages long. But at this point, I'll open it up for questions.
Yeah, John, thanks. Thanks very much. It was a bit like drinking from a fire hose, but I really do appreciate you coming and sharing your knowledge on and insights into attitude determination and control. One of the questions we have here is pretty early on in your talk, you alluded to a paper, sounded like it was a pretty fundamental paper by Malcolm Schuster. I know during the course of your talk, you actually cited a number of Malcolm's paper, and he truly was an innovator in this field, as you pointed out. That particular paper, I'm not quite sure it was referenced, but would you say that's a good starting reference for someone who's a young engineer or junior engineer at Goddard or any of the other NASA centers? Would that be a good place to, like your talk here, would it be a good point of departure to learn the fundamentals, or would you have to be a little more experienced to fully benefit from reading that paper?
I think it probably have to digest it. You probably have to. The estimation course in here is a 600 level course. It is because it involves a lot of optimization. You saw optimization theory here. You obviously saw probability and statistics. So, and then the dynamics portion as well too. It's a good starting point. Landis and I are actually writing a book right now, which hopefully will be a much better starting point.
Great.
But there's also, he wrote a book chapter in Pisacani called Fundamentals of Space Systems. I think that's a great place to start.
Ah, yes. I think I've seen that. Yeah.
I can also send a link. Malcolm unfortunately passed away last year,
Right.
But we do have his website. It's still active. Jim Wirtz is keeping it active. He's got every one of his papers in that website, and I can pass that along.
Well, that would be great. I think we'd like to make that available to people, and I'll put that on my my GNC community practice website as well. That page of quaternion identities, I think, would be a handy reference as well. A couple of general observations. I'd be interested in your thoughts on this, maybe more at a philosophical level. Number of the equations you went through are familiar to me when I originally early in my career working with star trackers. Nowadays, right, it's some of these star trackers, or most of them we fly, are starlight in and quaternion out, right? So all this mystery of or the mathematics involved in doing the attitude determination from the star sightings is lost. I'm a little concerned because I think it becomes kind of a black box for some of our engineers, right? And we lose some of the visibility. I mean, it's nice that you can go out and procure this, and it probably simplifies your onboard, attitude control, determination control system implementation. But it seems to me like you still need to know what's going on inside that star tracker. Any thoughts on that?
Yeah, and actually I wrote an entire paper on this. So the first question when I hear about that is, are they spitting out a covariance? And they usually say yes. And that's okay if you stick that into a filter. But the problem is this is something that Simon Julier and Durant White, who wrote the famous uncentered filter paper, came up with an algorithm called covariance intersection, is the correlations that exist on there. So what would you do in a column filter is you take all your stars that you get from each star tracker and put it into the column filter and process it, just like I showed in this presentation. You can take each one of the quaternions and do that, but the problem is, let's say I took two separate column filters. I took a column filter with the quaternions on one, and I used the gyro, and then I took another star tracker and the same gyro and processed that, and then I want to fuse those two pieces of information. I've just double counted the gyro. So that fused information is going to tell me I have more information that I don't have, and the covariance is going to be lower than that covariance that spits out from that fused process is going to be lower. So they wrote a paper on coming up with a way to fuse this without getting a lower covariance that's always going to be at least conservative. It's better to be conservative on the covariance than to be to say that I'm doing better than I really am.
Right.
And we wrote this paper on dealing with quaternion constraint, how you put that into the covariance intersection algorithm. That was what our whole paper was about. So yeah, I mean, it's the issue, but you got to be careful because you can end up with this double counting issue if you're not careful. If you just willy-nilly just use output from sensors, it's a classic thing. That's a lot of what our data fusion center spends time looking at. It's a classic issue in data fusion that it's nice, but then you also be careful what you wish for, because you always wanted this, but in the end you might end up with some problems.
Yep, just like any of the things we do, right? You got to understand all the assumptions and the underlying physics. I appreciate you making that point about pretty fundamental point you said about understanding the limitations of the math, of the models that we build, and that we derive our performance predictions. We have one last question, and is would you care to comment on? For a while back there, it was a kind of a hot topic, gyroless attitude determination systems, right? Where we're flying a full stellar inertial attitude determination system on a spacecraft. Maybe we could have, the goal being to save the cost, I guess, of the star tracker, typically expensive, not that gyros aren't, but flying, as I say, a quote-unquote gyroless attitude determination system. I'm sorry, save the money on the gyros, not the star trackers. Any thoughts on that? I don't know that we've talked about that so much today, but maybe that's a topic for a future discussion.
Yeah, something I did think about. I actually wrote a little technical note on this too.
Good.
I actually came up with a method that I can determine so one method to get the rate is to get the quaternion, take a finite difference to get Q dot, and then back out the angular velocity. But I found a method to determine the angular velocity without ever computing the attitude. So I wrote that up in a little technical journal, Guidance Control Dynamics. My whole thinking here was, okay, if you do this, you always got to take a finite difference somewhere. That's the bad news. And anytime you get a finite difference that is a derivative and that has 20 dB per decade in the magnitude plot, that's going to amplify high frequency noise. So the good news is you're going to get an angular velocity that doesn't have a drift. The bad news is you're going to increase the noise. So I did a simple back of the envelope type calculation as to, okay, if I sample fast enough, then I can filter that out. What level, how fast do I have to sample before I get to like a Cyrotep gyro. It was about 500 hertz. We're nowhere near that. I know Junkins down at Texas A&M, they've developed some trackers that are at 100 hertz. So the faster, the better we can get. Obviously, there's issues with light, incident light, and everything. I'm sorry, light.
Stray light.
Plane, yeah.
Yeah.
But as we get that hopefully we can have a star tracker be both a gyro and a star tracker. As far as gyro is, it obviously depends on the mission. My favorite little satellite just came down. That was Sampex. That flew sun sensor magnetometer, one reaction wheel, lasted 20 years.
Yep.
No gyros. So if you can do it without it, great. That'll save the cost.
Yeah, and like anything, it depends on the mission requirements, right? The
right.
attitude estimation requirements and pointing requirements. Okay, well, thanks. I think we've run out of time. That was a great talk. I think if there's any more questions that come in, John, what I'll do is make sure they get. You've agreed. I'll send them off to you, and maybe you can respond directly to the folks that are posing the questions. So this completes today's NESC GNC webcast. I'd like to thank you all for participating with us, and I look forward to you joining us again in March for our next GNC webcast. Thank you very much.